look inside my machines, you won't see many gears at all, but actually there are lots of them. It's just they're all enclosed inside gearboxes, particularly inside geared motors. By themselves, motors hare round at thousands of RPM, much too fast for anything I'm interested in, so I mostly use them with gearboxes attached. So the gears are hidden inside here. Then I also quite often use standalone gearboxes, and some of these I just get from the scrapyard. They seem to last forever. And of course a gearbox keeps the gears clean, and they can be full of grease, and they last a very, very long time. I hardly ever have trouble with them. But then there are occasions when exposed gears seem the right solution, like in the money laundering. The tower crane just obviously needed to have a geared mechanism like the real thing.
Lower the crane to the bottom to attract some cash. Now try to lift the cash to the top, but watch out for the financial regulators on the right.
Oh, we've patched things up and it's going on quite nicely now.
Now you've got to the top. Swivel the crane and deposit the cash onto the weighing scales by pushing the green button.
We have to move forward on this.
I'm not sure about that sector of the market.
So I like gears and thought they would be a good addition to my Secret Life of Components series. So the basics of gears are really quite simple. The teeth of one gear meshes with the teeth of another gear. So in this case a big one meshing with a small one. I'll clamp them together, I think. Won't have to hold on to them. So when the little gear goes round, it actually has to go round a lot more times than to make the big gear go round once. In fact, in this case there are 16 teeth on the little one and 120 teeth on the big one. It's a ratio of 7.5 to 1. So the little one has to go round 7.5 times, 7.5 complete revolutions to make the big gear go round once. That's really all there is to it. But the clever thing about gears is not only that they reduce the speed, they're also increasing the power, the force, the torque. So if this is 7.5 to 1 speed reduction, in theory it's a 7.5 times increase in torque, in power, and what you could lift, for instance, with the big one. And that's impressive. Even with fancy modern electronic speed controls, it's difficult to get that amount of increase in torque at low speeds. So I thought I'd like to demonstrate that with one of my very smallest motors. This is quite an expensive motor. It's a German Maxon. The motor's in the cylindrical bit on this end, and the black thing is the gearbox. This is a gearbox that I cut open, and the same sort of motor. See, there are a lot of gears in there. It's actually a reduction of 256 to 1. So there should be quite a big power increase. So this is one that I've without the gearbox on, so it's just got this gear on the end, but I can easily stop that with my fingers. It's got hardly any power at all. But I want to see what power it can have with the gearbox. So I made this little brass pulley to go on the end, and I'm going to see what I can get it to lift. So I've rigged up my motor suspended from the ceiling here with a cord, and I thought I'd try lifting a bodybuilding weight as something suitably heavy and see how that goes. Just fix that on there. Okay. So then we've got to put a scale so you can see how fast it's going up. Whoops, swinging about a bit, which is a bit more difficult to see. But you can see definitely that it's going up at a slow but steady pace. So because that worked, I thought, well, I'll try with 2 weights. Works just as well with 2 weights. So I was surprised. So buoyed by success, I then went on to 4 weights. So, yay! It just about works. It's going quite a lot slower, I think, this time. Oh, not too bad actually. I'm impressed. I underestimated it. Is there anything else I could just add to it to make it? Yeah. Okay. Well, I don't know if this will work, but 8 weights. Ooh. Well, it has really slowed down now, but it is still working. I'm amazed. I've run out of bodybuilding weights now, so I have to leave it there. So each of these weights is 1 1/4 kilograms, so 8 times 1 1/4, yeah, 10 kilograms. So yeah, really satisfying. So I was tidying up after doing that demonstration and realising that I'd rather underestimated the power of the little motor, and so that first demonstration, just putting my finger on the cog that came directly out of the motor, was really not good enough. So what I did, I went back and I've now made a second little pulley that fixes directly onto the end of the motor, and I'm using that to lift up some nuts. I have to hold it level. Anyway, I found that it would lift 3 12mm nuts, and they weigh 15 grams each. So even the motor alone will lift 45 grams. So the motor alone, at a speed of around 2,300 revs a minute, was lifting 45 grams. With the gearbox, its speed was reduced by 256 times to 9 revs a minute, and its load theoretically should have increased by 256 times to what worked out as 11,500 grams, or 11.5 kilograms. So actually the 10 kilograms it lifted is surprisingly close, because there are always some losses in practice. So the basic shape of ordinary gears is really quite subtle. When they mesh together, the points in contact are constantly changing, and the surfaces in contact, the points in contact, never slide over each other. They just roll over each other. So what I mean is that if I just take these 2 discs as an example, that is rolling, whereas this would be sliding. And gears like this, the teeth are called involute gears, but it is very hard to see. So then, of course, gears come in all sorts of different shapes and sizes. The one I use most is a size called 1 mod. So this is an 80 tooth gear, and the outside diameter is about 82 millimeters. But what's called the pitch diameter, which is the centre of where it meshes with another gear, slightly smaller, that would be exactly 80mm. I've got here an 80mm meshing with a 30mm. So the distance apart for the shafts to drill the holes would be half of 80, 40, plus half of 30, 15. So you drill the holes 55mm apart. And I don't know, I find that all makes it all much simpler to think like that. And I can't be the only person, because it's a very, very popular size. But of course, that it's not just one mod. You can get 2 mod, which are the gears I was just showing you before. So they would be, these are 20 tooth gears that are actually 40mm pitch diameter, and going the other direction you can get 0.5 mod gears, which would have twice as many teeth as the 1 mod. So it's a nice simple sizing system. And essential if you're buying gears, obviously. One of the remarkable things about gears is the sheer range of scale that they work at. So this is my smallest gear. Beautiful things. I mean, so tiny it's impossible to use the gears for anything else. They're just sort of little works of art, really. Of course, gears go even smaller. You get these, they're called MEMS gears, that are etched out of silicon, and for micro devices that are many, many times smaller. Then my biggest gear this is a 4 mod gear, and curiously I think this just came from a table for rotating animation under the camera. No need for teeth to be quite so enormous, but even this pales into insignificance compared with some of the really big gears that are made. I was looking it up and I found that nobody really is sure of the biggest gear ever made, but certainly this is a good contender, made by the Hoffman company. The gear was going to a copper mine in China, I guess for a ball mill. These break the ore up into little bits. They're vast things with a huge gear around the outside. Buying gears. Well, the cheapest and easiest to use if you've got just a really small load is to buy the gears from model shops. They're not as easy to find as they used to be, but you can still get hold of them, both just the gears or gears with a frame to fix to a motor and stuff. Much better are the old Meccano gears. I used them a lot when I was starting out. Though they're no longer made, they're still surprisingly widely available on eBay and not that expensive. I recently found the name Meccano comes from make and know. Very satisfying. But the sort of gears that I buy them online, and it's worth shopping around. The prices seem to vary enormously. The most common sizes are usually quite cheap, but then there are companies that specialise in more exotic ones, and these are just fabulous. The range is just extraordinary, and it sometimes is worth coughing up the money for some of this extraordinary stuff. So the sizing, how to work out what size you want. Well, going back to the beginning of the video, I explained about the mod system of sizing. So this is a 60 tooth gear of 1 mod, and that means that the diameter is 60mm. It's as simple as that. Yes, once you've got the size, then you've got to decide the material. There's obviously plastic gears, then there's steel gears, stainless steel gears, brass gears, and last but not least there are phosphor bronze gears. The phosphor bronze ones are the most expensive, but they've got a very good wear resistance, and so they're particularly good for worm gears where the surfaces are sliding over each other, and sometimes worth it. Finally, you can get gears with or without a boss, this lump on the side. I nearly always buy mine with the lump on the side, the boss, because it's really useful for fixing the gear to a shaft. So one way of fixing large gears to shafts, a traditional way, is to cut a keyway, this slot that goes through the bore of the gear. And then you also cut a slot in the shaft it's going into, and then you have this little key, it's called, that goes in there, and then they should just all go together. This one's a bit tight, I'd have to tap it on with a hammer, but like this, there's absolutely no way that the gear can rotate relative to the shaft, which of course is essential if the shaft is connected to whatever you want to power. But it's a fiddle cutting these keys. I had to do it by hand with a broach, and it takes quite a long time. So in practice I very rarely do it. For most of what I do, I just rely on a grub screw. There's a bit of work involved in this because when you buy gears with a boss, they don't have any holes in, so you have to drill and tap the holes. The other thing I think about using grub screws is it's always a good idea to put a flat, mill or grind a flat on the end of the shaft so the grub screw digs in there. This has two advantages. One is it helps keep the gear gripped on the shaft and stop them rotating relative to each other. But the other one is that if you don't, this grub screw has dug into the shaft and creates this really rough area, and that makes it very difficult, if not impossible, to put a gear on and off later on. For plastic gears, you can sometimes just use a shaft that's a little bit oversized and force it on, because there's enough sort of elasticity in the plastic. Another variation of that's used a lot industrially is to knurl the end of the shaft and then force it in with a hammer. And that produces a very strong grip. Then the final technique, which I find particularly useful for fixing a tiny pulley or something to the output of a small motor, when it's really too small to put a grub screw in, I just use a high strength Loctite. Just got some on the screw here, and then just push the pulley in. You want to try and keep a little bit of a gap at this end so that the Loctite doesn't go into the motor bearing. Let me go a little bit further than that. But that is surprisingly strong. That's exactly what lifted the 10 kilogram bodybuilding weights. Once you've got your gears mounted on shafts, then you've got to get the two shafts the right distance apart and parallel to each other. Well, if you haven't got a metal shop like mine, you can do this with wood. Hardwood makes quite a good bearing surface. It's actually rather hard to get the mod spacing accurate just with a ruler. So this is a low-tech way that I've sometimes found works better. And I should have said, it's important to do this on a drill press. This means that when I drill the second shaft, it will be parallel to the first one. And then put the other gear on. so that it meshes nicely. The other shaft, if you grind a point on the end of it or turn it in the lathe, it can act like a centre punch. So you put the other shaft in here and you literally just give it a tap with a hammer. Back to the drill press. So now we'll see if this works. That goes in there like that. This one goes in there. Oh, it's looking quite good. Yeah, that's looking promising. And that actually meshes pretty perfectly. So anyway, that's a low-tech way of doing it. But if you've got metalworking tools, I tend not to have the two separate plates, but to have just one plate and then a tube which will take a second bearing at the end. So I'll turn little things like this, and then this is the plate that I've already cut a right distance apart, and the recesses take the little bits of tubing. The recesses just help hold it all together precisely when I weld it. But first I've got these little bushes, oilite bushes, that I hammer in. I'll do it on there. So that's my kit. So I'm just going to weld this all together now. So there we are, that's one of them. Put the gear in there. And now, and so there they are. Yeah, one more thing about spacing gears. Although they'll probably work at a variety of spacing to some extent, the trouble is if you get them too close they grind against each other, it's noisy and they wear. If you get them a bit too loose, the gear can wobble a bit, and this is called backlash. A small wobble like this is not a problem for many applications, but it can get amplified. So I thought I'd designed Microbrake to be so the movements of the chair and the carpet would be smooth, and that when it stopped it would be, they would both be quite rigid to make it easier to get on and off, but actually it's really quite wobbly, and that's due to backlash in the gears. This is the worm gearbox I bought, and you can see the output and the linkage to the carpet wobbling about. A good example of how backlash can get amplified. For light loads like measuring instruments, there are anti-backlash gears. These are actually two concentric gears with little springs that keep the teeth lined up with each other. But you can tension the springs and force the two gears to line up on adjacent teeth, So when they mesh, the teeth are pushing out against the sides of the worm gear's teeth, preventing any backlash. If you really push hard enough, you still can get some backlash, but for instruments that's not usually a problem. And beautiful things. Industrially, most gears are made by a process called hobbing. The cutters are similar to the taps for cutting screw threads. So I decided to have a go with one of my taps. I put it in the mill and the gear blank, free to rotate, is in the vise. When they mesh, the tap magically starts to cut the teeth. I should say I tilted the mill a bit so the tap's teeth are at right angles to the gear blank. Initially it just cut a dished shape, so then I realised, of course, I needed to move the mill table in and out to get the flat profile of the teeth. Unfortunately this was less successful. I hadn't really made everything rigid enough. I think I'll stick to buying my gears ready-made. However, gears don't always need to be that precise. The beautiful old wooden gears in watermills and windmills certainly could never have been precise. I made this clock 40 years ago when I didn't have many tools. Behind the dial it's a mix of bike chain and hand-cut gears. I cut them with an angle grinder. Oh, and this is the winding mechanism when the weight reaches the bottom. More recently, after I bought my CNC plasma cutter, I tried cutting some gears with it. After a few failures, I got it to cut reasonable teeth as long as they were 1.5 mod or larger. Anyway, good enough to make this simple automata a present for a friend. We both love estate sales. Of course, today you can use a graphics program or a CAD program to print out a template. I particularly like this gear generator program that can even make complete CAD files for involute gears. I use this for my estate sale automata gears. And of course, with a laser cutter, the gears can be really precise. Well, so far I've just been looking at the most common sort of gear called spur gears, but there are lots of other sorts. There are pin gears, historically very important, and used on clocks, and people still use them on automata and that sort of thing. Things that go round fairly slowly without too much load. Pin gears don't need to be too precise. Another experiment, I tried marking these out just with a compass and dividers. The pins are 1.6mm welding rod pushed into 1.5mm holes in the plywood. Then there are gears that are completely straight. These are called rack gears. And of course you can either move the rack or you can move the motor. So So what I thought I'd do is to look at some of the other sorts of gears that are most interesting in more detail. Worm gears can be very, very simple. You can just start off with a bolt or a bit of threaded rod that has the same pitch as the thread and the pitch of the gear wheel. And then, well, that's really all there is to it. I've mounted one here so it can spin round, and then here I've cut off a little bit of the threaded rod, put it in the drill, and round it goes. I've actually got a very basic worm gear like this in my garden. It's in the clock. The project I did with Rex and another friend 40 years ago. And Rex made the actual guts of the clock based on the flywheel from a car. The big wheel here with the teeth round the edge that engaged with the starter motor originally. But he adapted it so at the bottom here he turned a worm gear out of brass. In the clock it just moves the hands round once a minute, just a bit, a few seconds. One thing he did do, which perhaps is partly why it's lasted that long, is that if you, I don't know if, yes, if you can see that the thread obviously on the threaded rod is obviously inclined. So to get the rod to mesh as good as possible with the wheel, it's best to tilt it a bit. And Rex did that in the clock so that it's in contact all across the width of the gear wheel. But even so, this would really only work for very light loads. If you want a worm gear for high loads, you need to buy custom-made worm gear sets like this. So these are rather beautiful things. You can see the teeth on the wheel. They're inclined at an angle, and that's so that the two shafts can be quite accurately at 90 degrees to each other. And then the other thing is they're dished in the middle, they're sort of curved. And the reason for that is that there's more area in contact with the actual worm, and that helps them carry heavier loads. One of the reasons I like them is because you get such a dramatic speed reduction in a small amount of space. So to demonstrate that, I'm going to mark one of the teeth, and now I'm going to turn the worm round by one revolution. I'll put a mark on it there. Okay, that's one revolution, and you can see, fairly obvious really, it's just moved the wheel on by one tooth. Well, this wheel has 24 teeth, so that's a reduction of 24 to 1 in a really compact little space. If you were to do that with spur gears, you'd either have to have an enormous wheel or several stages. The potential of worm gears to reduce speed is astonishing. This exhibit at the Exploratorium in San Francisco, made by Arthur Ganson, has a motor that's connected to a chain of 12 worm gears, each one going slower than the one before. It ends firmly bolted to this block of concrete. It's never going to move in our lifetime. So that would actually take 13.7 billion years to rotate once. Blimey. Another thing I really like about them is the way they lock. So there's, like this, there's nothing that would move that wheel. So if you think of the demonstration I did lifting the bodybuilding weights, that means that when the weight gets up the top and you switch off the motor, the weight will stay there. And this is unlike spur gears. These are the model I had at the beginning of the film, and with this it's very easy for the big gear to make the little one whiz round, even if you had two stages. So then you'd lift the weight up to the top, turn off the motor, and then it would glide back down to the bottom again. So that sort of locking is very useful. Having said that, there are some worm gearboxes that aren't self-locking where the worm has multiple starts, so that it's much steeper angle. And I've only got one that in my collection, although they are useful things. Mine is in an old wind-up gramophone, and here, what's even odder about this, it's being used the other way around to increase the speed. So it is the wheel, which is attached to the main spring, is making the worm go round. This is to power the governor that controls the speed on the sides. And actually there's two stages. There's another one just hidden in here, so it, which gets it up to the right speed for the governor. It's a lovely thing. Yeah, so anyway, lots of good things about worm gears. Another sort of gear that's very useful is a ring gear with the teeth on the inside. And this is particularly useful used in conjunction with an arrangement of ordinary spur gears like this. So here the central gear is connected to the main shaft, and the three outer gears are mounted on a disc that rotates round the shaft. And then the ring gear, oops, just slips over the top. So to show you what it does, the ring gear is usually held stationary, and the input to the motor is through the central shaft. So that's one rotation of the shaft, 2, 3, maybe just less than 4 to 1. Still, that's quite a big reduction. But the really great thing is that you can stack these up. So that little gearbox that I had at the beginning, I've stripped it down now, lifting the bodybuilding weights, that had 4 stages. So what that does, it has these plates that hold the 3 gears around the outside, and on the other side of the plate is a central gear to mesh with the 3 gears of the next stage. So this gearbox had 4 stages originally, each one reducing by 4 to 1. So that's how you get the 2, 5, 6 to 1. It's 4 times 4 times 4 times 4. A wonderfully impressive big reduction in such a small space. But I should have also said transmit a particularly large amount of power, because they've got 3 gears, they've got 3 times as much area of contact, and you're not taking all the load on the single tooth. So yeah, a lot of power as well. This motor, that's actually off an electric drill. In fact, all battery drills have epicyclic gearboxes inside. And one way you can tell an epicyclic gearbox is that the final shaft comes out the middle, sort of in line with the motor at the back. Planetary gears can also fairly obviously be used in reverse. So in that case, the input would go in onto the disc, and then that would increase the speed of the central gear by the same ratio, 3.5 to 1. And like this, they're sometimes used on wind turbines. The gearboxes on wind turbines are extraordinary things. They're under such loads and they have to run continuously. I don't think anybody's really quite settled on the best design yet, and I think they still provide quite a lot of problems. Yeah, a difficult thing, because you have to step up the speed for the generator. It can't work at the slow speed that the blades go round. Of course, gears aren't just useful for reducing speed. They can do quite a lot of other things. Those 2 simple gears that I showed you at the start show how they can reverse the direction of rotation. So if the input is on this gear, the other gear will be turning the other way. And you know, this is unlike if you use a chain or a belt drive where the input and the output go round in the same direction. Then if you want to change direction of rotation by 90 degrees, you can use these special gears called bevel gears, which are, the teeth are cut at a 45-degree angle. I rather struggle to use these bevel gears. They push each other apart as they turn, so if they're under any load you do need quite good bearings, but I've rather taken to just buying a bevel gear box in situations where there is a significant load, as I did with the divorce machine. This silvery lump in the middle, that's a bevel gearbox. So the shaft from the handles comes in and is turned round by 90 degrees. Then there are gears that are cut on an angle. And these are quite common. Angle grinders have angle bevel gears. The motor is down here, and so have to change the direction of the drive by 90 degrees. So inside, this is one I just cut the top off because the motor had burnt out, and there is the angle bevel gears going from the motor to the disc. There are quite a lot of them inside cars, so the differential, the crown gear, is cut on an angle, and inside the main gearbox most of the gears are cut on an angle. So the advantages are that the teeth are more continuously in contact and have a bigger contact area, so they can take a bigger load, and also it makes them quieter because with a straight cut gear you're going from one tooth to another, so there's some more chance of vibration. The downside is that it's no longer an involute gear, there is some sliding between the gear surfaces, and that the gears push each other apart sideways, the force of the gears meshing. So the shafts need special bearings, taper bearings or thrust bearings. But all the same, they're still widely used. For very large gears, originally designed for ships, so from the engine to the propeller shaft, they developed these herringbone gears, beautiful things that have two opposing angles to cancel out that sideways force. So combinations of several bevel gears can do quite clever things. This is the differential gear from a pickup truck. So the prop shaft there going to the engine, and these two are simulating the wheels at the end, the rear axle if you like. So as I showed before, there's the big angled bevel gear in there. And I'm amazed the scale of that gear. I know pickup trucks are a bit bigger than cars, but obviously has to transmit a lot of power. But the additional feature this has got, which you can hardly see because they're hidden, is that in here there's some more gears. And you notice that when I turn this wheel, the other wheel goes in the other direction. So because they're all hidden in there, I thought it's easier to see with the differential from a tiny radio controlled car that I've got here. Instead of the prop shaft, it's actually the axle is powered in these little cars. So you've got your three gears fixed to the axle. this is one of the wheels, goes in there, and this is the other wheel that goes in there. So now if I hold that, you can see they do exactly the same thing as the wheels were doing on the full scale differential. So what's the advantage of this? Well, it's quite simple really. When you're going round corners, the outer wheel has to travel further than the inner wheel, and so to avoid wearing the tyres, by superimposing the forward motion, rather than making the two wheels go in opposite directions, you can just slow one slightly, and that will increase the speed of the other one. And this happens sort of automatically. So it's very clever. Differential gears actually have quite a few different uses. They were even used in the Second World War as part of mechanical computers, analogue computers, for aiming guns on battleships and things. So in that case, the inputs to the differential were what were the wheels in the car, and the output is the prop shaft. So the sum of the two angles is the angle that the prop shaft will turn. So if they turn in opposite directions, sort of plus 30 degrees and minus 30 degrees or whatever, the sum will be naught. But if they both go, say, 90 degrees in this way, that'll go around a lot further. The ratios aren't quite perfect to do an accurate result here, but that's the idea, is that the angle there is always going to be the sum of the two angles on the inputs. 3, 2, 1, go! A few years ago, when I got excited by differential gears, I was also reading about doping in sport, and the combination of the two turned into this machine, Supercycle. Using differentials and lots of other gears as well wasn't the quickest or easiest way to do it, but I did quite enjoy it. So the two differential gears are at the bottom, actually from golf buggies. The one on the right is adding the two speeds of the inputs from the cranks, and that gives the speed that the scenery goes round. The one on the left is subtracting the speed of one crank from the speed of the other one, and that controls the relative position of the two bikes at the top. So gear mechanisms are amazing things. For many years I just couldn't resist picking them up when I came across interesting ones. Things like this. Well, this is actually the mechanism out of an old twin tub washing machine to make the impeller go backwards and forwards. Needs quite a lot of power to slosh all that water around. Just another random example. This is actually an aircraft instrument, and I don't fully understand what it did, but the gears are just beautiful, and the amount of skill in designing and making something like this is extraordinary. I used to have a lot more things like this, but I found I never ever used them. So eventually I took them all to the scrapyard. And making this video though, I now rather regret it. There's something, they may be obsolete, but they're still fun. And you can puzzle out how they work just by fiddling with them in a way that you can't with today's digital electronics. But probably I'm just a bit of a dinosaur. Anyway, I wanted to end with these completely extraordinary gears. You can't really believe that they could possibly mesh with each other, but they do.